right, question 1, the stone is dropped from the top of a cliff. So wouldn't it take a certain amount of time for it to hit the water? And then the splash it makes, which is the sound, wouldn't it take a little bit more time to come back up? So there are 2 times involved, but what's given is the total time. That is the problem. So the 3 seconds that's given is the total time, which should be the sum of T1 plus. That is why it's going to be a math problem. It's not a physics problem as such. But can you give me an expression for T2? T2 is the time taken for sound to come back up. Doesn't sound travel with constant velocity? Let's take it as 343. So if the height is h, which is what you're trying to find, if the height is h, what's the time taken for the sound to come back up? H divided by 343. Hello, time is distance divided by speed. So the time for sound to come back up is going to be the height divided by 343, right? Okay, let's get it ready. And then I'll show you. Okay, let's talk about T1 now. How do you find the time taken for the stone to hit the water? What's the initial velocity? 0. So, and you're going to use the king. Some of you don't know what the king is. It's the equation that's most often used. Delta x is equal to v naught t plus 1/2 at squared. Don't worry, I'm going to show you everything. And I just want you to see that the first term vanishes, isn't it? The first term becomes 0 because the initial velocity is 0, and then you have 1/2 times 9.8 times t1 squared. Are you with me? So we have our set of equations. All we need to do is substitute one into the other and solve. And that is a pain. So I'm going to do it for you. And I will not try to ask this on an exam. I will not try. Because it's more math thing than physics. So T1 is the time for the stone to hit the water. That's the equation that I'm talking about. That gives you h is 1/2 g T1 squared, isn't it? Because the first term becomes 0. Because the initial velocity is 0. And then T2 is the time for the sound to come back up. All right, and that is, and the total time is the sum of the 2, which is given as 3 seconds. So I'm now trying to substitute. That's all I'm trying to do. Because we have set up our 2 equations. And you have to substitute and solve it, isn't it? So all this is going to be hectic because the squares are involved. Look at that. T minus T2 whole squared. Because T1 is T minus T2. Put that back into that. You know that when you square something, A minus B whole squared will be, it has 3 terms, isn't it? A squared minus 2AB plus B squared. So you have 3 terms going to come up. You know what I decided to do? I decided to write in the numbers later on because it was too hectic writing 343 all the time. You see what I did just now? Not a mistake. I just did not want to keep writing 343 till the end. So I just said, I'll plug in at the end. So I solved that. That's why I said it's a pain, because I have to get a quadratic equation now. And to get a quadratic equation out of that is tough. Now I have got the quadratic equation. Do you see it? Well, it's easy to copy down. But you see that h squared, and there's an h term here. Okay, so it's like ax squared plus bx plus c is equal to 0. And then I have to solve it. I'm putting the numbers now because I know the velocity of sound. That's what I get. And then I solve it. I did not want to show you all the stuff that I did. I'd solve it to get 2 answers. The first one, because a quadratic has 2 answers. One is 26,028 meter and the other one is 41 meter. Which one would you pick? Okay, 41 meter, of course. That is how you get that. All right, so you have to look at the given equation, look at the general equation for pressure changes, match them up, and you get lambda, because lambda is 2 pi by k. Second one, frequency is omega by 2 pi. Omega by 2 pi. So now you know omega is 1350 pi. So you get 675 hertz. Just have to look at, I'm sure everybody's able to understand, right? Okay. And C says the speed. How do you get the speed? If you have the frequency and the wavelength, how do you get the speed? Just multiply them. Or you could even go this way. Remember this formula? Speed is omega by k. And either way you get it. And then pressure maximum. Today I'd given you the formula for pressure maximum. 2 pi rho VAF. Because you're asked to find the displacement amplitude. So we're trying to find the displacement amplitude. The density is given. Displacement amplitude is A. So make A the subject. Substitute all the others. I save you a lot of time by calculating. And this is the answer. All you got to see is whether you can make out maximum pressure from there. 2 pi. Density. Velocity, which we already got. Frequency. The reason why we put it in decibels is to get a better understanding of how we perceive sound, correct? But when you do problems, you always have to have it in the proper units, which is watts per meter squared. Okay, so that's the first thing I'm trying to do, trying to change 120 decibels into proper units, which is the I. All right, dividing by 10, beta by 10. Then you know that the opposite function of logarithm is 10 to the power. Does everybody know that? Just like the opposite of natural logarithm is e raised to, right? Same way. The opposite function of logarithm is 10 to the power. So if I take away logarithm from the right side, I have to have 10 to the power on the left side. That is what I'm doing now. So 10 to the power beta by 10 is I by I naught. Therefore, I is simply I naught times that. And we know the value of I naught. You have to know it. I naught is always 10 to the negative 12. You've got to know it. And beta is 120. 120 divided by 10 is 12. Therefore, you get 1 watt per meter squared. That's the first thing we do. Change the decibels into the proper units. After you get it in the proper units, you can try to find how much wave energy is contained in each 1 centimeter cube volume of air. How do you do it? Yesterday, didn't I give you a formula for energy in terms of volume? Yeah, we did. Look at this formula carefully. Isn't that the definition of intensity? What's intensity? Intensity is, actually it's energy per second per unit area. That's what I've written. Energy per second per unit area. Surface area. We were using S, trying to stick to the textbook symbols. And therefore, to find energy, all you got to do is rearrange. And then you know that delta T, which is time, is distance by velocity. See all the substitutions that come in? Okay, therefore, there you go. Answer. Now, there is a problem here. The problem is you need to recognize between caps and the small. How I try to do it is I try to put a ribbon on top if it's a small letter. You see that? Just don't go by the size. Because one represents velocity, the small one represents velocity, the caps represents volume or change in volume. Does that make sense? Change. That's why you have change in volume and velocity. Number 4. That's the formula. We're trying to find I. So I'm using that ready-made formula because last time I gave you that, right? So you put it back into that, you get 10. You get it? At 10. And then divide 10 by 4 because there are 4 engines. So it's 2.5. And then convert the 2.5 into decibels. You take the log of that, and that's 12.39. So you get 123.9 decibels, which is 124 decibels. So for number 5, you need to remember this formula, 2 pi squared, velocity. Again, you see the small letter. So density, frequency squared, and amplitude squared. You're asked to find the intensity. First, you get it in proper units, then change it into decibels. Direct substitution into the formula. Of course, you'll be given the speed of sound. If not given, always take it as 343 meter per second. You see that repeating? Because that's the speed at 20 degrees Celsius. 1.29 is the density. Frequency is 380, that's given. Amplitude is 1.3 times 10 to the negative 4.
So we don't do 1,290?
It's 1.29 kilogram per meter cube. It's the density of air.
Yeah.
Okay. Yeah, for 1 second I said, what? I thought I had made a mistake too. Okay, and then you get the intensity in decibels. Okay, number 6. We're running out of time, so that's the guitar problem now. Number 6. An unfingered guitar string is 0.73 meter long and is tuned to play E above middle C, whatever it is. It's 330 hertz. That's the frequency. So the length of the string is given, isn't it? Length of the string and the frequency. And the question is, how far from the end of the string must a fret be placed to play A above middle C, which is 440. So that length plays 330. What length do you need to play 440? That's all, isn't it? Okay, what's the relation between length and frequency for a vibrating string? The relation between frequency. What's the formula for fundamental frequency of a string? N is equal to V by 2 times the length, isn't it? So don't you see that's inversely proportional? You have the frequency on top is equal to velocity by 2 times the length. Okay, here it is. If you couldn't see it in the air, now you should be able to see it. Frequency, what's I saying, N? Yeah. Oh, long time back I used to use N as frequency, so it keeps N. Frequency F is equal to velocity by 2 times the length. So it's inversely proportional. So when you put it as a ratio, isn't this how you write it? Yeah. F1 L1 is F2. Or F1 divided by F2 is L2 divided by L1 because it's inversely proportional. And that's all. What an easy question. So all you got to do is there and you get the answer. Stop. But what did the question ask you? How far from the end of the string must it be placed? What you got now is the vibrating length, isn't it? It's the vibrating length. So if it's already 0.73, don't you have to take the difference to know where you have to put the finger or the fret? Okay, that's why it's 0.1825. That's the answer. What we get is the vibrating length. On the second one, or the B part, what is the wavelength on the string of this 440? Okay, you have to find the wavelength now. Wavelength, you had to know that for a fundamental frequency, wavelength is twice the length. Remember that? Lambda by 2 is equal to the length. So lambda is 2 times the length. Twice the length, and you get the B part. The C? Please answer that. What is the frequency and wavelength of the sound wave produced in air? This was the frequency in the string. Now the question is, what is the frequency that goes out into the air?
The same.
Definitely. It's a shame if you don't say the same. Same as the string, 440. The wavelength, this divided by 440, which is 0.78 meter. Didn't I tell you yesterday that the frequency does not change? I even gave you an example of light. And I can't remember the colors that I talked about, but I told you that blue light, if it goes from air into water, it will still remain blue. Frequency never changes with the material. What changes is the wavelength and the speed, which you see here. Didn't the wavelength change? In air, but in the string, it was different. That takes us to number 7. It's about pipes now. So, and first you got to find the speed of sound at 15 degrees Celsius, which is what I did just now. It's 40 meter per second, sorry. So you got the speed, now you got to find the frequency of the fundamental standing wave. Do you see the word fundamental there? Anybody remembers the formula? For fundamental in an open pipe? V by 2L. Yeah. 2 times the length. For a closed pipe, it's divided by 4 times the length. So remember that. This question is about an open pipe. Therefore, open pipe, fundamental is this. Therefore, rearrange and find the length. The frequency is given, you find the length. And the C part says, what are the wavelength and frequency? Oh, you also have to find the wavelength, can't you? It's like before. What you found is the length of the pipe, isn't it? You remember how the fundamental wave looks like in an open pipe? Antinodes at both ends. Antinodes at both ends. What's the distance between 2 consecutive antinodes? Lambda by 2. So couldn't you put lambda by 2 is equal to this length? Because you know that you have antinodes at the 2 ends. Okay, that's how you find out. So therefore, lambda is twice the length. You get 1.30. Stop. Okay, 1.30 meter. Now the same kind of question. What's the wavelength frequency in the traveling sound wave produced in the outside air? The frequency will be the same. And what about the wavelength? What was inside the pipe? What was actually vibrating? The air column. And what's outside? The air. I mean, the material is the same, so everything will be the same. Okay. All right, so that takes us to the 8th question. Same. I think I did not write down the answers to the C part, but I told you, right? It's the same. That's why I didn't write it. Maybe I forgot. Anyway. 8th one. All right, remember what we did yesterday? You take the difference. Remember? Take the difference between the two. So 616 minus 440, and then take the difference between 440 and the other one. And you find that the difference is equal, so 176. And just look at this explanation, don't copy. For an open pipe, be with me, please. For an open pipe, 176 could be the fundamental, but overtones are integral multiples, right? Remember that? And do you get those 3 numbers as integral multiples of 176? No, the answer is no. That's why it's not an open pipe. I'm trying to prove that it's not an open pipe. I hope somebody understood. No? Okay, so 176 Not the case here. They are not integral multiples, so this is a closed pipe. And then I think I tried to prove why it's a closed pipe. I don't remember. Maybe I did not. Okay, for a closed pipe, what's the fundamental frequency? Formula. Lambda over 4, okay. For a closed pipe, remember that they're only odd integrals, so it's okay. So fundamental is 88. The fundamental is 88. 88 times 3 is 264. 88 times 5 is 440. And 88 times 7 is 616. All right, number 9. That's the speed of sound at 28. 347.8. That's the speed of sound at 28. And therefore, you find the fundamental. Is it talking about an open pipe? Is a flute an open pipe or a closed pipe? Open pipe. Now realize that if you didn't know that, you wouldn't know which formula to use. You're in trouble. Okay, so since it's an open pipe, it's V by 2L. Therefore, velocity divided by twice the length, that's the frequency. Now at the second temperature, this is the speed, and find the fundamental corresponding to that one. You get 253, and number of beats in 1 second, remember, is the difference between the frequencies. Therefore, it's approximately 10 beats per second between these two. At the end, but first try to understand. Well, the fundamental formula is F prime is frequency. You remember that formula? And then you have to draw the diagram. That's my bat. Okay, what you saw just now is sound waves moving towards the listener. That direction is taken as positive. Source, which problem am I doing? Is it number 10?
The object moving away from that.
Yeah, I don't know what I did. Bat at, oh yeah, a bat at rest. Hello? What's the bat doing? Nothing. That's why I had to take a fresh look at it. The bat as the source is not moving, correct? The bat at rest sends out ultrasonic sound waves at 50 kilohertz, receives them returned from an object. Okay, the object is moving away. You see that? The listener is the object moving away. Just stop there and tell me what will happen to the signs in the formula. Which sign will change before I show you? Well, Vs will become 0. Everybody knows that. Now, the only question you have to answer is, will the sign of the velocity of the listener change? Or will it not change? The direction of sound waves towards the listener is positive. And is the listener moving in the same direction? Yes. So the sign does not change. I tried. This is always a problem for students. If it's in the same direction, you multiply with a positive. That's how you see it. You don't put a positive, you multiply with a positive. So the sign doesn't change. Okay, now it's easy. If you got that, that's easy. So that's the formula that works in this case. And just plug in the numbers. You get the answer. Okay, is there a second case to that? Yes, there is, because it says, read the question. It says it's received them returned from an object. You see that? So there is a second case. I'll let you write down the first case, then we'll go to the second. So in the second case, it's reflected, so it's moving towards the bat. All right, what's that? The object is still continuing in the same direction. Isn't that the idea you get? Yeah. But the direction of sound waves towards the listener, isn't this the listener now? Is taken as? Now, if this is the positive direction, don't you think that this is negative? So therefore, the sign of the velocity of the listener will change. Okay. That's all I can do. That's all I can do. Is that understood from the formula? But then there is a velocity of the, okay, don't write, don't be in a hurry. Did you really understand this? What's the velocity of the listener? Okay, that's why the top part, you get a 0. And what's the velocity of the source? Okay, that's why the sign changed, right? No confusion. Okay. And I got it as 42 kilohertz. Is this something like this? Is that something like that? Or did I make a mistake? Well, you could have drawn it either side, you know that. Yeah. The listener for me is here, not moving, the source is moving. Direction of sound waves. But sound is always produced by the source, okay? Don't laugh, but some people don't know that. Sound is produced by the source. Therefore, sound waves from the source to the listener is positive. How will the formula change before you see it? What's the velocity of the listener? 0. So the source, do you have to change the sign? No. That's it. Easy. You don't have to change the sign, except make that 0. And there you have the formula. Substitute. But does that give you the answer? No, because the original frequency is not given, and neither do you know the apparent one. So well, you can do it. What did you say? Add to what? It's better that you write a formula for beat frequency. This is the actual frequency. This is the beat frequency. Now, look, don't miss out on this. Isn't this automobile also producing the same frequency? So wouldn't he be hearing both at the same time? He would be hearing his own, and he would also be hearing this coming from the other, right? That's why there's beats. And the beats will be the difference in frequencies, right? Correct? And the difference is just f prime minus f is equal to whatever is given. What's given? Yeah. So that's the second equation. Now you have two unknowns. You can solve it. That's all. F prime minus f is whatever is given. 4.5 in this case. Substitute and solve. $97.82 is the answer. Well, yeah, the 12th one is done. Just like 11, try to find out from the diagram.